just don't know whether it's by nature that when you're a student you have to do some funny things sometimes, or whether I am the one who is too overzealous to care about you, to care about students. Which one do you think is which is which? Am I too overzealous that I care about students too much, or is it that when you are a student you have a special issue? Which one is which? Are you too busy to do a couple of things that you are supposed to be doing, or which one is which? Which one is which? So I only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of the 27 that normally sign this sheet, having been the ones who have filled the registration form. And you are on where you can't say, if you aren't on where I would say fine. You aren't seeing the form. So when I design the form, put it on where tell you to feed it so that I can get to know my students and I plan for them, and you don't feed it, what am I supposed to interpret out of that? Let me see those who are here. Moves, actually, moves. Because you said you are on moves. Okay, so why haven't you filled the form? You filled it, but the photo refused to upload.
So I do not submit.
But you can only submit it. So how do you submit before you upload, or you submit? When do you submit? Which one comes first? Submitting and uploading. So why did it refuse to upload? Because it is clear, it tells you the files that you can upload.
I was standing from there. Starting there,
Where what?
I was taking a photo from that using the camera option on that exact space.
That's new technology. How do you take a photograph in a special film? How does that work? You take a photo, save it on your phone. When it reaches the time of uploading, you upload the photo from your phone. Okay, so I will get, I'm going to waste 10 minutes just to rant. So those who are here, that was Mwezi, and Rashid. I know you said no ID, whatever, but we agreed you put a police letter or anything that if you can have a university ID, at least you put a national ID or any document that shows that you are so and so. Then later on, when I'm checking, I can say I don't see your exact, because I cannot know your registration number, your student number, if I don't get them from the ID. Shakir, what is the reason? You are just, there's this current saying of, so, let me tell you, scratch me, the way you scratch me is the way I will scratch you. And I do it on record. I normally don't beat around the bush. I spend time to care about students. If you don't care about your degree, I'm gonna care about myself. I want to earn my salary with ease. The consequence is you enjoying the course I'm passing. I'll do my part. Good enough I do it on record. Okay, I want to hear from this one has just gone out. He has no reason. Mahat, what is your reason? Nothing. Okay. Hakim, why haven't you filled the... Even to enroll, I had to first quarrel. Then you enrolled immediately. So why haven't you filled the form?
I'm filling.
Hmm?
I'm filling now.
Okay. So I'll be quarreling. So if I don't quarrel that you pass, will you fail? Nasuma is married here. Arafat, you're also feeling now.
No, the challenge is with the ID.
So what happened in your ID?
I kept it somewhere, so I had to go back. I was feeling it, but
You got a loan? I heard the president say that Manaland has now taken national ID, so he took your student ID or what? Okay. Up to here. I want to make sure everybody gets a chance to tell me what is going on. Sinabuya. Sinabuya. This one is run out. Sinabuya is there. What is your reason?
I'm not working on this.
Hajar. Shamil. Oh, you don't know even what I'm talking about. Oh, you know. But you don't care. I know, but that is your problem. Okay. Kasa Adam. And Jeremy.
When I was thinking myself, it's the independent.
They said you bring it to me or what?
I always believe in this, but I think my notes are
So what are you going to use to take the photo?
I started marrying now, I'll take a pic and then I'll say.
No, you had your ID those days. Where is the form filled from? From the phone. So you had left your phone here or?
It's the ID work.
Eh?
It's the ID. I realized as you were filling in the form, they needed the photo of the ID.
And you had your phone.
I had my phone, I did not have my ID.
Who can explain to me? Which language do you speak best so that you can speak it and understand? You had an ID where you were.
No, where you are.
Eh.
I put when you are the number.
When was this? Because this is fifth week.
It was the previous week.
And I put the form even before the semester began. Of course, you could not access it when we began the semester, but everything was ready. And the other ones haven't arrived. Once, not soon. You first sit. First get a seat. But you know terms and conditions apply. Kabuli, since you are back. What happened? Why haven't you filled the form? You're going to fill today. Aren't you the one I put in front? Not today. What's wrong today? I said forever. I said forever. And if we shall be using this room, I can even make sure my camera is this actually. Okay, if you had filled the form, I would have cancelled it so that you see it anywhere. But you have not filled the form, so what is the result? You sit near Kasad and face Kasad is not the problem. You have a seat, you have a chair. You sit there where Kasad is. I have 2 minutes to go to finish my ranting. I'm asking people why they are on the way. I put a form there to fill and they haven't filled it. And this is the form that informs me who is my student and their details. So let me see. Nabukonde has filled, but I think you lodged my lecture on Tuesday. You have evidence? So, Nasun, I'm still waiting for the answer. Where has issues? Like how many? Like how many? I want to know so that I see where I can help. Like how many? So the others I will check later if I find that. So just to ease your way out of through the course, on the top of the course where there is welcome to PHY whatever here, and then there is a click here. Here is a hyperlink. This one is hyperlink. Hyperlink means that if the word you are read, it could be either green or whatever. You see it wanting you to tap on it and it takes you whatever it wants to take you. So this is click here, I think for the form. So you click here, it takes you to the form. And also I put in small. This is small. I think this is reddish and big, but these are small and black. So I have put there, click here to access the course study materials 2024. I've been having a challenge that whenever I teach the course, then I have to restructure. And then every week I'm putting new videos. I have old videos, then I have these new videos. So I have gotten an eye trick that every year, if I'm to teach a particular course, every year I will be having a link to pages for that course, for that year, especially the videos, so that somebody can compare if they want to compare. All along I was only sticking to 2013 playlist. And sometimes, although it is still interesting, but there are things which I have changed the way of explaining. So please click here. This is also a hyperlink. Sometimes there is an underlining of such links. You click here, it takes you to the course materials. We agreed, we have references, all the books are there. Notes, all the notes are there. It's a one-stop center. Videos, the playlist for the videos is there. And I have all the notes again on YouTube. So you cannot say that I'm not on where, so I can't access notes. As long as you're on YouTube, each of the playlist videos has a link, a PDF link below. And so, those who normally, people used to say, we can't see what you are writing on board, especially those who are not my students. So I put a PDF, so that you can, when I'm already chopping and writing as I talk, you can read through the PDF as you follow. So I spend all this time to do all this stuff. And you can't click and feel a small page like this. Just because you can't, you know, the problem is that you don't want to show your ignorance. You can't take a nice photo of your ID, so you can't take the photo. So you can't fill the form. So you pretend you keep doing like this, but you are not, you are just refusing to show your ignorance. You don't want to show that you are ignorant. If you don't show ignorance, then you can't learn. It's until when people say you don't know this, then you learn how to. I'll tell you a funny story. We had a young man who had been helping us. They had brought him now to help us on looking after the boards. So we went to watch magic. Is it magic or how do they call it? These people who used to, that's where I learned how to shake my chest. Is it shaking? Yeah? So there was this, I think he was a military guy, you know, going through the room which is having fire around. So, but there was this man who dances like this, made of boxing. So when that young man said, I'm going to make that thing. So when he reached home, he tried, he failed. Because he had told me that he knows how to make it. So he tried, we cut stuff, he failed. So I made it. And up to now, I still make it. Whenever I get a chance. Pardon? I have a photo, I think, and a video. I have a photo and a video making it for somebody. So, I don't know, maybe just tell me the truth. If I am over caring about you, I can also reduce and do other stuff. You just tell me you are overworking yourself for us. We don't give a damn. Then I also learn how to program my time and use it for things that make me happy. Although teaching you and you understand makes me more happy. Because when I meet you and you are like, because all the people have taught resistant magnetism and electromagnetism, teach it in secondary. And for me that is an amazing thing. I didn't want to tell you the lady who actually taught it at the university when I was still teaching in Chambo, but that's not my idea. I mean you, the first thing is to go to secondary. So last time, we were able to get the work done being the same as epsilon r over 2 integral over tau e squared tau. And we had wanted to do an example where we needed to find the, I need to be sure, where we needed to find the energy due to a spherical shell having charge Q. Example, find the energy of a uniformly charged spherical shell. Spherical shell is like a basketball. So if the cover of the basketball was mainly the charges, and then of course you saw, let me just repeat it. But is this where I stop? So find the energy. Find the energy of the uniformly charged, spherical shell, of total charge Q, and radius capital R. So as a solution, if we can get the electric field intensity, then we can fit it in, we know the term in spherical coordinates, then we can fit it in there and get the energy. So the most thing to do is to get the energy. So how do we get the energy? If we have a spherical shell, having a charge state positive as a default charge for our distribution, you can shade it if you want. And then it is of radius capital R, the total charge. This is a spherical shell. Of charge capital Q, small q. So what is the first thing to do in order to get the electric field intensity? Because that's what is of the importance in our expression for the energy. What is the first step? Zafar, if we have a charge distribution, no matter how it looks like, as long as it is symmetrical, and we want to find electric field density that this charge distribution is, giving out, what do we do? Good, very good. So we apply Gauss's law by creating a fictitious surface that mimics the charge distribution, and that one we call it a Gaussian surface. So we create a Gaussian surface that is encompassing our charge distribution, and once we make this Gaussian surface, which is spherical, so if this Gaussian surface is of radius smaller, then we can use, or we can apply Gauss's law and find the electric field intensity. The moment we get electric field intensity, we substitute it here, and then we find the energy. So applying Gauss's electric flux theorem or Gauss's law, then we will have the integral ds equaling to the total charge enclosed over epsilon naught. It is in free space, so this would be over epsilon naught. So this one will be, so the electric field density is radially outwards, and then on the surface of the on any part of the spherical shell on the surface, we have, if we chopped out a small surface area of the enclosure, then we have this vector coming out perpendicular to this surface, also in the same direction as the electric field. In other words, if I took this to be this spherical shell, so if I just try to, shade it to make sure that it is looking spherical, and I choose just a part of this as the area ds, then this being the vector ds is also coming from, so also we have the electric field intensity along the same path. And so our dot product would be the electric field intensity, magnitude, then dot. So it will be integral over this closed surface S. Then we would have E magnitude, ds magnitude equal to that. But so we will be having E outside, then the cosine of the angle between them, ds and E are, E and S are parallel. Then the angle between them is 0. So the cosine of the angle between them would be, so I will be having this, and this would be equal to that. So what is the surface area of this spherical surface that Gauss advised us to use? So I have, this is 4 pi r squared. So we have E is equal to plus E is equal to 1 over 4 pi epsilon naught q over something that we would have taken as if this is our charge we have as the spherical charge distribution or shell. So it would be that charge over. So if you were to be at a distance, a good distance away from this shell, it would be acting as a point charge. And the electric field intensity due to the point charge is the same as 1 over 4 pi epsilon naught, that charge over r squared. So we got E. So we want to find the energy. So the energy, I don't know whether we use W or we use E. So we can't use E. E coincides with the electric field intensity. So the energy W is equal to epsilon r over 2 integral over the volume tau, and then we have our E squared. So we have our Q over 4 pi epsilon r squared tau. But the tau equals to those of you who can find out the tau in spherical coordinates, equals to I will trust you. So then I substitute it. And then, because this is our volume, so we shall integrate each of these, the dr, the theta, okay, the r along theta and along the azimuth. So this would imply that W is equal to epsilon r over 2. Then we have Q squared over 16 pi squared epsilon r squared. Then we have integral The radius goes from where to where? 0 to R. You can only have the electrophilicity felt up to the, okay, it is felt further, but the radius we are looking at is up to the, so we have 0, the capital R, then we have, this is R squared, and then down here we have R to the 4, so it is R squared, R to the 4, dr. Then we have the angle. The angle, the zenith angle will vary up to this point, from here to here. Because once you go again this side, you are experiencing the same field with the same properties like the one which was going this side. Because a given field will be coming from the charge. If this is the charge, one part of the field will be going this way, another one in the same opposite, directly opposite will be going this way. So if you have taken care of this, you can't again look for it this side. If I have a point charge to draw its field, I'll be having this one here, which is exactly opposite to this. This one here, opposite to that. That one there, opposite to this. This one here, opposite to this. This one here, opposite to the other. So if you have covered this whole part, if you commute, you are again doubling this one which you have already taken care of. You are again considering what you have already taken care of. You are also considering, so you can only move from 0 to, so we got 0 to pi, sine theta, theta, and finally the azimuth. The azimuth is you can only have a chance to go around the equatorial part of the sphere in order to make sure that you have covered the whole shell in its bed. So that means you'll be having the phi from 0 to 5. The rest is algebraic gymnastics. So this would be the same as so this is 2 pi, this is minus cos theta, then 0 to pi, you put in the, then, but before I go that far, this goes, the other 2 pi goes, let me first weigh here. So this is a half q squared over 16 epsilon naught pi squared. Okay, this is 1 over r squared, which is minus 1 over r. And then from that means it will be 0 to r, that means it will be minus 1 over r plus 0. Is it minus or plus? I have already said it is algebraic gymnastics, so I'm going to do your stuff. So this is 2, and then if you raise 2, you add 1 to the index divided by the new index, which will be minus 1. It's 1 over. So we have the capital R emanating from this part. And then we got a minus plus pi, which is 1, minus cos, what is cos 0? And which is 2. So then we have a 2 here, coming from where? This is 2 pi. So this goes, and this one goes, and therefore I'm not good at dropping numbers on the board because I'm not supposed to be, I don't want to show, I'm not supposed to be proving anything to you. It is you who is supposed to be chopping these things in your own vision. I chopped my things really big. So sometimes, so it would be the same as therefore, W is equal to Q squared over 8 epsilon naught R. Okay, so
Yes.
How is it get a confusion when it comes to integrating 1 over r squared in the limit from 0 to r? We get minus 1 over r, but if we put in the limits where there is, we shall have 1 over r.
no, I think the integral, the limits on this one, we got them wrong. The electric field, there is no electric field inside the shell, okay? So that means we start from the shell, the cover, and then we can stretch until where the charge can help us reach. Probably where? Up to infinity. So about that. So it should be up to infinity. Yes, you can, if you have a strong charge, you can make it go to infinity. But infinity is subjective. It's like being rich. If you are near, if your neighbors are all poor, and you have a wheelbarrow, they all come to borrow a wheelbarrow if they want to do some construction. And they say, Mugaga wafe. Now if you are staying in Kololo, that's why rich people, when they meet each other, they just say, how do you do? And I hear the answer is, how do you do? So some guy say, how do you do? I say, I do well. He say, no, that is wrong English. I told him, I tell you how I feel, not how you think I should tell you. So for the rich people, Muyanga, Kololo, when they meet each other, they say, how do you do? How do you do? Because they know everything is okay. There is insurance, they are in a Range Rover, they have, they are sure of the terminal benefits or the retirement benefits, so it's not a problem. But Katanga, when you meet each other, they say good morning. Actually, not even good morning, it is how are you? Because what is good in the morning that is not yet even. Am I speaking French? So have we, I'm sorry about the limits. Limit for R, this R, the shell. Inside the spherical shell, here, a hollow conductor. The E here, inside the whole of this, E is equal to. So that means we always start from here at R, and then straight. But we use infinity because we can't limit ourselves to even 10 meters or whatever. We make it open and go up to infinity. And then you do your mathematics, since you are good mathematicians. Now, this energy here is tricky. The charge is uniform. This one was uniform. It was a uniform spherical charge distribution in form of a shell. So if I got a charge distribution, it is birally meaning that it is rugged. Here I have more charge according to corona discharge. Here, not more charge. Then, why is it using? It is not supposed to use the air. Yes. So I have a high charge here, high charge here, less charge here. So I cannot be sure of my charge distribution. I need to use something that makes me comfortable. Just like in Nakasongora, cows vote. So the population in Nakasongora is very low. In Wakiso, even you can't manage to have a chicken. There are no cows, but people are too many. You can't even find a cow. They don't have where to put it. So if you are to compare Wakiso and Nakasongola, you can only use density. So you talk of population density. Because if you are going to use the numbers, then you get a problem. The same thing we were talking about when we're looking at the energy that is felt in between the plates. For example, capacitor. You cannot know where, because if you got a capacitor, you have your plates here and another plate here. Yes, the moment you put your battery and you have designated this other as a positive and this other one as a negative, it's okay. You may assume that you got a bunch of these positive charges here and a bunch of these positive charges here, but remember, when you go towards the end here, your field becomes non-uniform. So you find that you have uniform field probably in the middle here. But you're looking at a capacitor, when you are drawing the energy from a capacitor, and you are using it to play music or to run whatever gadget you are running, it is not going to be saying, yeah, we want to draw from the middle. It draws from the whole capacitor. So these other ends are also contributing to the same problem. So you would be more comfortable if you talk of the density. So the energy that is stored in the middle here in the electric field, you look at the density because the energy at the end is less than the one which is in the middle. And there is no way you are going to isolate these other ends. And it's like the batteries. If you are having a torch, because these days you people, I don't know, anyone of you who has a gadget that uses batteries, dry cells? So not many, because nowadays the radio is on phone, the torch is on the phone, the calculator is on the phone. So, but if for us who were using the rudimentary dry cells, if you get one old dry cell and you put it in the middle of new dry cells, assuming the radio was taking 4, and then you have one fake one, one old one, and then the other 3 are new. Everything goes down because of the nano resistance of this one. They will be struggling to stream their current through this other fake one. And that's why they normally say that the efficiency of the group depends on the most inefficient person in that group. So don't be there and you are like, yeah, I'm smart, I'm going to make things happen. They're that stupid one who is there in the, it's like in the family, if you have that one brother or sister who is a nuisance, the whole family, that's why the ancestors were very clever that whether you have engineers or you have pharmacists, if you have this drunkard, this one drunkard, makes a name of your family. You mean the family of that boy who sleeps each after he has drunk. So we are better off if we use the energy density. So that's why we want to know this part. So energy density in an electrostatic field. The energy required to assemble, if we go back, the energy required to assemble, the distribution so there are 2 options once you got the distribution of charge. You got the charges which are within the volume. So you have the charges which are inside here of this volume. And the energy due to the charges in this volume here, they will give us the energy, which is a half. Remember this expression here when we revert back. So we shall have a half integral over the volume tau rho v tau. This is due to the volume, the charges inside this volume. But then also we got the energy due to the charges on the surface that is enclosing the volume. Yes? On the? They have. We got that in our distribution. We had to use the half to make sure that we do not count charges twice. And then we changed it into we brought in the volume charge density and got that expression as that. So I expect you to remember that. After we got the summation, then I should never equal to J, then eventually we wrote it as a half integral equals to a half integral rho v tau. This is for the volume, the charges due to the charge density inside there. Now, due to the surface here that is enclosing the volume, we have the half integral over the surface S sigma v ds. So we are in and out, okay, or in and around. In a volume, rho v beta, around the volume, around our distribution, the sigma v ds. Chibira, have you seen it? Yes. Good. So once we got this, of course, where rho is the volume charge density, where rho and sigma are the volume, and the surface charge densities. Respectively, and V is the potential that is experienced. V is the potential. But when we have such charges in there, these charges have a relationship with the electric displacement. So we said that, or from Gauss's law, when you are moving through this volume, then we have that the divergence of how far you can diverge the electric fields depends on the charge density and the permittivity. On the other hand, if you are to see it in the form of the electric displacement vector, then the divergence of D will equal to rho. So, but rho equals to divergence of D, and on the surface, we have this electric displacement vector being normal to the surface. This electric displacement vector, which is being distributed as you diverge it through the volume, and when it reaches the surface, it is believed that it will be perpendicular to the surface. Because the electric displacement vector is related to the electric field intensity, and we say that for any distribution of charge or any charge, any conductor, the electric field energy is perpendicular to the surface. Now the moment we got this, and then we got them here, so now we can say that our energy is now equal to a half integral over the volume tau. This is now divergence of D, then V d tau plus a half integral over the surface S, and then we have D that N roof, then ds as our other part. You can be completing this with algebraic gymnastics. Substitute. So so there is no break. Yeah, I've taken my break away. It's just 11 now. I should, those minutes I spent going up and down, I should have used them for our break. So you've already, where are you now? So that I go on. You are just here. So this would imply that this is equal to a half. Okay, so we have the divergence of D, and so from the identities, if you remember when we were trying to find the energy previously, this work done here, or energy, and we had rho equal to divergence of D, and then we used the expression for the oh, there is a V. There is a V before ds.
Yeah, very good.
By the way. Rashid. What do you mean by the way? I went away, you should have realized that. That's why I said you can go on from there. So we use the vector identity, using the vector identity. Since you don't seem to want me to go with you, let me go with myself. So using the vector identity, divergence of dv. So the divergence of dv would be equal to d, would be equal to v, divergence of d, v, divergence of d, then plus the vector which is d dot the new vector which would be the gradient operator times the scalars, which is scalar potential. So according to this identity, this is a vector identity which will be provided to you in identities during test and exam, so you don't need to cram it. You just need to know how to use it. I'm not teaching you to cram stuff. I just want you to understand the basics. Yes?
I'm confused. I thought potential is a scalar quantity.
Yes.
So how come we are working with it as if it's a vector?
Because the gradient operator is the same as I kali by kali x plus j kali by kali y plus k kali by kali z. You just wanted me to say kalis. So once you have this and then you multiply it by v, then it becomes kali v by kali x plus j kali v by kali y plus k kali v by kali z. And by the look of things, this one is a vector. But we never, in the books you find that this is a bit shaded. And some crazy authors who want to be special even put a vector on it. So the gradient operator is a vector. When multiplied with a scalar, the product now becomes a vector. And that's why we are able to dot this v with this vector here. Clear?
But we are happy the potential V as a scalar. Then we have the electric displacement vector. So if you have a scalar, the operator value is operating on dV. Then how come that we shall have that?
Is this a vector, yes or no?
Yes. Yes.
Is this a vector now, yes or no?
Yes.
That's how. Is this a vector, yes or no?
It's a vector.
So have I done any problem having this vector and not into this vector? This is mathematical methods in physics. What did you do? Are we clear? I want to go on. I'm just being nice. I didn't want to say this is a mathematical methods in physics. Go look up to it. I didn't want to do that. So then we have we can now substitute for this divergence of d here as v divergence of d being the same as divergence of dv, and then minus d dot grad v. Okay? So I can first put it here for granting. This implies that this one here, v, okay. Divergence of d, to make things look the way they are supposed to look, is the same as divergence of dv then minus d dot grad E. Substituting for that in my expression above, I am sure now you are appreciating what I normally mean by algebraic gymnastics. Here, nothing so special. We are just now trying to make sure that we get our way out. But there's nothing physical, like there's no physical interpretation I can use to explain to you why I'm doing this. I'm just trying to derive eventually what I want by making sure that I use vector identity. But here, from the other side, we looked at the volume and the surface enclosing it, and then we got that, then substituted for the charge densities, that here, and now we want to make sure this gives us something better. So you now, our energy will be equal to a half, and then integral divergence of, so this whole thing became this. So I'll be having integral divergence of over tau, so the tau remains around, so this is divergence of d tau minus integral, sorry, it's still and a half, integral over tau, then d dot, dotted with grad v, d tau, and then I add on the other part, which is a half integral over the surface S, and I can have the d dot ds. So I can have the d dot ds. N dot n ds equals to ds the vector, because now the n makes you understand that it is perpendicular to the surface. That's the only purpose. It has no magnitude. Yes. I use the negative. Where? Here. I have it here. What? I have this identity, then I wanted to find out this, which is here. Then I made it a subject. So I take the other one, the other side, it becomes a negative. And then this is the problem I've experienced. Whenever I make things simple, explain from first principles, then I get issues. So when I chop and chop, everyone is comfortable right there. So I'm used to this kind of, when I make things simple, questions, how could you make that one uninterpreted? So then we have this one, M. This M and ds means that if you had a surface which is ds, and now you are having this the unidirection vector that is protruding out of it, now this will make this ds, this end roof will now give us a ds vector normal to that elemental surface area. So then we'll be having d dot ds, and so we can have our v somewhere there. Doesn't matter. It's a scalar. How you arrange it is up to you. So far, so good.
So come in the second integral, we are putting the v this side to work as a scalar, and we can do it for the first time.
Which side? It doesn't matter whether I put it on which side. If I wanted, I could put brackets and put it this side.
No, I'm saying from the other step where we have either u as a half.
Where? Here?
Yes.
Yeah.
So then in this last step you said you can scalar function.
This one here?
Yes. But then in the first integral we said we have had to derive from this other vector identity.
Yeah.
Yes. Couldn't we also bring the v this side to just get the divergence of v only?
Like you want me to put a v here
Yes.
and get the divergence of d?
To give it as that. Because in the second...
This identity says that when you are having the the divergence of a vector times a scalar, it gives you the scalar in divergence of that vector plus the vector dotted with the gradient of the scalar. This is the identity. I didn't make it. That's what those guys who hustled gave us identity. So it's this identity that I made this one a subject to rhyme with what I got here, and then substituting my expression here, which I did around here. So I don't know what you are choosing me over now. Yes.
It is a statement that is confusing, so we should just ground it.
I said so. I said this is given in a test, this is given in an exam. Even now you got it. If you have the notes, it is in the textbook. I should have said on page this, that identity. Yes?
So lift from the explanation, we have the side, we have a ds sum, a ds and then the normal intellect. And as we're trying to draw them as if they're perpendicular to each other, and then they're
When I got a Benon surface area, which we call ds,
yes.
and then I multiply it with the normal unit vector, then it gives me the direction of the vector to that surface.
Oh.
I've already told you that I am having a surface, an elemental surface, and that elemental surface, they are telling me that there is a normal unit direction vector to that surface. And that means it can give me the vector to that surface, which is my ds the vector. And my ds the vector, this ds the vector is the same as that vector normal to that surface that is along the unit direction vector. That's it. It isn't changing anything. It is not going to change anything on my surface, but it is just giving me a vector that is emerging out of my elemental surface. And this is because mostly we shall have on a surface electric field lines emerging out of there. So it helps us to understand that that's how the electric field density is behaving. Any other concern? Slowly you'll understand that the reason we teach mathematical methods in physics is that our times we had issues. You will be doing electricity and magnetism and doing vector calculus too. You are doing Green's theorem in math, you are supposed to apply it here in physics. You haven't even understood it in math, and now they want you to apply it here. So we said we need to change and teach our math, which is relevant to our physics. That's how mathematical methods in physics was introduced. By experience of how I have been teaching these two courses, electricity and magnetism and electromagnetism, it seems you are doing math in mathematical methods in physics. And there is no reference to the physics that you are supposed to be applying it to. That's my analysis. Whether you are doing differential equations, you are supposed to be doing an integrator and a differential option of the either operational amplifiers and the capacitor circuit. And then you do integration, but in relation to the physics. But I cannot teach in mathematical methods in physics, then teach electricity and magnetism, and then teach electronics, then teach electromagnetism. Can I go on? Yes. I just go. So now I have this, I have this, I have that, and this looks a little bit familiar. So, but the mean grad V equal to minus 2. So that is done. Now here, this is a volume. This is a volume according to TWINAMASIKO Benon theorem. We can, since this one, once we put here an E, it looks a bit fantastic. Then we can look at how we can make this have a brother. Okay, have something that is similar to it. This and this can be made to look the same. Either change it to a volume, change this to a volume integral, or change this one, this one, a surface. We don't change to the highest, we keep it low. So, this one here is done, so now I change this one, It's diverging, so now I make sure that that vector dv, I dot it with a ds, and then I would be done. Is that the case? How do I change this to a surface? No, I will do. You will also do. When you are in exam, you will do. So you keep quiet, I will do. So this one is, once you have this, you change it to a surface. We just get that vector, then dot it with surface. So this would be the same as a half integral over the surface S, then that vector, which is d dot ds, then I add on so this is minus, grad V is minus E, so this becomes plus. So plus a half integral over the volume tau, and then I have d. I thought I wasn't seeing my vector there. So I have a d dot E, and then the tau. And then I add on, a half over the surface S, d dot d. This a half plus a half gives you 1. So I have this being the same as integral over the surface S, v dot ds plus a half integral over the volume tau, d dot e tau. Even if I think I write it like this, I have no problem. You are lost.
Yes. From you is equal to half. Integral over the surface v dot ds, where from where it is transited from the volume to the surface.
When you are changing, if you have changed this one into a surface, what do you do? When you have divergence of the vector tau, and you want to take it back to a surface, what do? You get that vector dotted with the surface. That is TWINAMASIKO Benon theorem. I don't know how you make Linda's back to dog. But at least the Benon theorem can change the door, Okay, so maybe I should have stated it as Kaumai saying that using TWINAMASIKO backing theorem, using here. Is it here or here?
Here.
Using TWINAMASIKO backing theorem. Support me so that I can patent it and then it goes into the textbooks. Anyhow, my next textbook of electromagnetism, I will put it there. Whether they want to do whatever, they will read it and use it.
We don't want our kids to make cakes.
We don't want your kids to make cakes. So, we've, this half and half has made this one, but this is what happens. For larger R, okay, when R is very large, radius, if we are considering, for example, a surface which is a sphere, and we have this sphere having a large radius, that means that the volume, the potential is the same as the charge over 4 pi r. So it varies as 1 over r. This one is the electric displacement vector, which is more or less like the electric field intensity, apart from just adding an epsilon r. So this d varies as 1 over r squared, because it is the electric field intensity 1 over 4 pi epsilon r squared. This ds is the area, which is r times r. So it varies as r squared. So for okay, so this implies that our v d dot ds would vary as this times that. So this would be, they would cancel out, so it would be vary as 1 over r, which would tend to 0 if you have a large radius. That is for r tends to infinity. So that one also disappears. So when it disappears, we remain with this baby here. Yes.
How come that the conditions or the assumptions only apply to the first degree, not apply to the second one?
If you apply to the second, maybe it will be 1 over r to 4. But what we will remain with at the end of the day, we want to have this. We want to have this. It's like saying that, I don't know which good example I can use to be.
So I thought assumptions would apply to all of them.
No. We apply assumptions to what we want. If you go to a family with many girls, you look for one you want. You can't say they are all here. Isn't that the case? Even if they are twins, unless if you are so confused that you can't differentiate them. But if one has like a scan, you can identify it. You just choose that one, unless if you allow it. Hence, okay, the issue is that we are being selfish. We want to find the energy density, so this one is already diminishing if we are considering such a kind of charge distribution, and so that will be able to help us get what we want. Yes.
My question is that why are we only changing the volume, the volume integral, and not working on the one of the middle one? Because we have only changed the first one.
We are not. We we know what we want. That's why I said when you go to a family, if you go to a family and they have too many sisters, there are many sisters, you say, I want Jane. Do we have a Jane here?
Yes.
Okay, scholastic. You say, I want scholastic. Even if this other young one or old one who is more beautiful comes, you say, I want scholastic. You don't change the topic and say, it is okay, you have come. You understand?
Yes.
Are you sure? Yes, you don't look somebody who you run in the trick. Ladies use that trick that they want to see whether you are faithful or not. So anyhow, I don't know how I should explain this. We are trying to find the energy density, and after doing all that we have done, we end up with this other part. Because we need this energy density within this volume. But once we look at the other parts, which have now merged to that part, if we look at this charge distribution for some kind of long distance, then it ends up having this other part going away. And then we remain with this one. We can also change it to a surface if we wanted to get something out of it. If changing it to a surface would help us get something. But as it stands, so hence the integral in the book, in the notes, it is a closed surface VD dot MDS will be approximately 1 over R, which will tend to 0 as R becomes larger. And then we'll get that thus our energy density is the same as a half integral over volume tau d dot. We did this in electricity and magnetism, but you were not very keen. This is energy. So the energy density is the same as the energy over the volume, which is du tau. And if you are in a grading and now you differentiate, then you do nothing. Therefore, you get a half d dot, thus, or whence, or therefore, our energy density is equal to a half d dot. And if you want to be so stubborn, you can say that this is the same as epsilon e squared. True or false? If you want to be so elaborating, D is the same as epsilon E, therefore energy density would be the same as a half epsilon E dot E, therefore energy density is equal to a half epsilon E squared. So now we know a couple of things about charges, how they produce electric fields, how we can quantify these electric fields in terms of getting the electric field intensity by utilizing Gauss's law. And then eventually when Poisson and Laplace came in, they now also brought in new things. So from the Gauss's law, which we have comfortably applied, especially in this last example, for so substituted for the E, and then got the grad squared V being the same as minus rho of epsilon naught. But the divergence of the gradient operator to the scalar gives the Laplacian, which is the same as in the regions where you don't expect any charge density. Then you have no charge there. There is no charge there, but there is potential there. And there is electric field density hence in this kind of places. So if you have such kind of configurations, you don't have charge particularly, but you are having the potential there available by, for example, if you had the potential on these plates. Of course, indirectly you cut the potential. You can have the potential without the charge, but not in the existing form that you have. That's why we are looking at discrete charges, then continuous distribution of charges, because it helps us to know where are we in these different configurations. So now we are going to the next section of the course, which is going to show us the actual algebraic gymnastics. And this is the solution of potential problems using Laplace's equation. And this is the section that made me forgive Laplace for his meanness of just saying that in the regions of no charge density, then you have Laplacian grad squared V equals 0. Am I hearing an excuse me? Or? Hey, that's soon. I will now bring you here in Florence. Hey, if you continue mumbling around, I will now bring you here.
She's complaining about TWINAMASIKO.
The theorem. You don't want to write my name in your books. Hey.
TWINAMASIKO is so called Gauss.
Yeah?
TWINAMASIKO is so called the Gauss.
No, I don't know what Gauss. I don't know what Gauss was talking about. I don't know how Gauss made a surface become a volume. Do you know how? He just says if you have divergence of D, then the tau you can change it into D dot ds. But TWINAMASIKO says if you have dough, if you have made paste, and you have cut pieces which are, surfaces, and you dump them in your cooking oil, then you make Linda's something which is having some good volume.
I interject.
You interject.
I interject. That thing is already a volume. You see, it has the length, the height.
You could make it small. You've seen pancakes.
Of course, there will be some small thickness, but not the whole.
So I understand, but even paper, which I've been using as an example of the surface, it has thickness at a microscopic level, whether they are nanometers or whatever, it's there. So you can say volume, but this is a real volume, like Linda's, It becomes a volume, and which has a significant way. You can't just say this is much volume. You can't say I'm going to get this multiplied by this. So it's an arbitrary volume with a volume charge density, and that's where I get in. I will explain it and be adapted. As for this course, don't say Gauss's divergent theorem. It is TWINAMASIKO and Benon theorem. Fame. Agreed? Any question from the previous part? Because now we're going to go on a roller coaster. This one I will not be over-explaining. I will be chopping. Yes?
Okay, my question is still with that statement we are using. I thought we are changing our volume into a surface.
Yeah, you can. It's a reverse way of doing things. whatever had it gone to the volume, we can know that it came from the surface.
Now my question is, when you say using...
You want me to flatten the leaders to a door again, or?
Yes, I thought there is another theory that can change the volume.
There's nothing like another theory. When you come from one area to the tax park, and you use the same route, you can. But there is a problem. Someone, I think, made a joke that some guy was complaining. From here to Entebbe is 3,000. Entebbe to Kampala is 2,000. Why? So the guy says, from Monday to Friday, is it the same as from Friday to Monday? How is that? Is it the same? Monday, you are Monday, Tuesday, Wednesday, Thursday, Friday. 5 days. From Friday to Monday is Friday, Saturday, Sunday, Monday. Where is the fifth one? So, well, please, I don't know whether you want to argue with me or whatever. I propose this just to make sure that we can remember this is ring theory. It's not by force that you have to write TWINAMASIKO ring theory. But I think it explains the point better. And I'm going to fight hard so that, remember in that two-stand magnetism, when I wanted the charges to be taken the way they are supposed to move, not the conventional way they move. But as you know, someone is saying the system is rigged. These days I've learned how to just enjoy my life without hustling. This year, if I manage to reach December without posting anything on Twitter, will be the best year I have enjoyed, but with pain. Sometimes I'm watching a TV show and then they are talking nonsense. I get the phone when I have typed, I remember I'm not supposed to post, then I drop the phone there. It's painful. Those days I would make my opinion be heard. And sometimes even journalists will come here to interview me just because they saw my post.
It ceases to be the best year.
So it ceases to be the best year. No, that is to me, but externally I have not had issues. I'm free.
That's true.
No one knows even what is going on with me. So we are done with this. I need to remove it so that we don't remember anything about it. This I should have made sure that this is done last time. I don't know, because of your late coming, this is why now today I was supposed to start from here on the solution of simple. Do you want to make, should I say simple or keep them just problems? Okay, keep them problems. So, solution of problems, so potential problems, not that they are potential problems, but one of potential, the work done to move the charge from one point to another point. Solution of potential problems using Laplace's equation. Using Laplace's equation. So this equation, this section here, made me forgive Laplace. Otherwise, I was going to write an article about him. How?
One point you said you write a text and then where you have attacking problems, you never put it there.
This is not my curriculum. I can't say nice things. I'm supposed to teach you problems. But if I write a textbook, I'll not put there problems. I'll put there something like inquisition or inquiries or something like that. Problems makes it look a bit problematic. So Laplace's equation states that equation states that the divergence of the gradient operator times the scalar operator, so grad squared V equals to, but the Laplacian is the same as the divergence of the gradient of the scalar. This one here, this is the Laplacian, which is grad squared V. This is Laplacian, but this is Laplace's equation. So we're going to look at it in three coordinates: Cartesian coordinates, spherical coordinates, and spherical coordinates. That's the reason why I was answering during the course outline, to show you how these coordinates look like. And I assume that you understand. If you don't understand, or if you don't remember, the video is on. So in Cartesian coordinates, then the gradient operator is the dot product of the I Kali by Kali x plus j Kali by Kali y plus k by Kali by Kali z. So that means that the Laplacian grad V would be the same as this one would be Kali squared V by Kali x squared plus Kali squared V by Kali y squared plus Kali squared V by Kali z squared. And because the Laplacian's equation is the same as Laplacian equaling to 0, so this would be equal to 0. The form of this similar form in cylindrical and spherical, the form of the Laplacian in cylindrical and spherical coordinates, will be obtained by using the expression for the divergence, and gradient operators. In these coordinates. So if you go to the textbook by Griffith and you try out the calculus part of it, then this Laplacian here, the Laplacian here is given by the divergence of the gradient of the operator. So this is you first get the gradient operator in spherical, then dot it, take its divergence in cylindrical or spherical, and then you get the Laplacian. You get the Laplacian, and when you make it equal to 0, you get the Laplacian equation. I have no time to do the divergences and the gradient operators. You do it in your free time or when your revision time. So in cylindrical coordinates, then we have the Laplacian equaling to 1 over r, Kali by Kali r, in r, Kali v by Kali r, plus 1 over r squared, Kali squared v by Kali r squared, sorry, Kali phi squared. This is the azimuth part, and then has the z part, which is Kali squared v by Kali z squared. This is the Laplacian. Once we equate it to 0, we get the Laplacian equation. In spherical coordinates, then we have the Laplacian grad squared v being the same as 1 over r squared Kali by Kali r in r squared Kali v by Kali r plus 1 over r squared sin theta Kali by Kali theta in sin theta Kali v by Kali theta plus 1 over r squared sin squared theta Kali squared v by Kali phi squared. And of course this would equal to 0 if we are now looking at it in terms of the Laplacian equation. I'm painfully going to work on something that I won't finish, and it is unfair. Just because we missed a step last time, and then today we have spent so much time in deriving the energy density as we went around. You don't need to cram this. You can derive it using the gradient operator in that coordinate and the divergence of that gradient operator on the scalar or on the potential in that particular coordinate system. This one is simple. You don't have to wrestle that much. Now, remember, in the due course of finding the potential, sometimes we are going across the boundaries. So like we are crossing, if we are in plates, for example, then we are looking for potential, then you have the potential in the middle of the plates. And then you have, so assuming in the middle of the plates of, for example, the capacitor we put in the dielectric, then the potential will vary. Or just if we are moving from this kind of arrangement with the potential to another arrangement of a different potential. That means we need to know the boundary conditions and then start with understanding these boundary conditions using the uniqueness theorem. Is that differential equations, or where do you study the uniqueness theorem other than mathematical methods of physics?
Dynamical systems.
Okay. Electromagnetism, and we electromagnetism now, so I can't be asking and then you say it is here. You say that these people, whether it is a joke or not, but we are asking, is this the chairman's place? So boundary conditions. And the uniqueness theorem. We want to find out that if we had a potential having two values, and these two values are all satisfying this equation here, how are these two values related to each other? There, that's where we get this idea of uniqueness theorem. If two values are satisfying the same equation, then there must be something unique about these two values. Or is it factorization or quadratic equations? You've got these two solutions. You have two solutions giving you the same value, but they are two. There must be something unique about these two. So we start by the uniqueness theorem. This is one of the most viewed videos, one of my, with some case. I don't know why it attracted some case. There are some videos of mine which I don't understand what they were looking for. Those who have watched it, unfortunately they don't leave that much comment on it. I have one with 7K. Even if I was to teach until I retire, I may not teach 7,000 students. But I don't know what the people who were watching that video, what they were interested in. It is a solution of Laplace's equation by separation, I think separation of variables. I don't know whether they were looking for the simplest way of understanding it or something like that. But it is 7K. The one I love so much is about the Brood's model. That afternoon or whatever time it was, I think I was very satisfied. So things were just flowing. It is about 3K. Do you know what I'm talking about, or you just? So how do two solutions of Laplace's equation? How do two solutions of Laplace's equation concur if they both, is this the spelling? If they both satisfy the same boundary conditions. This is what we want to prove. We want to prove if two solutions are satisfying the Gauss's equation, Laplace's equation, how do they concur? So, as proof, we want to prove that if we got any two solutions, V1 and V2, they concur and they satisfy the Laplace's equation, there must be something unique about it. So let V1 and V2 solutions of the Laplace's equation. So if there are two and they are all solutions, this would imply that the grad squared V1 is equal to 0. So V1 will satisfy. And so would be V2. would also satisfy the Laplacian equation. Hence, taking the Laplacian of the difference of these two solutions, V2 minus V1, then we would have that grad squared V2 minus V1 is equal to. So I just want to look at, I just don't want to go any further because I want us to start from here tomorrow when you are fresh. Yes? You go to Google. It is, okay, here what I wrote is concar, this is O. Con, C-on, Q-U-O-R. Is it E?
It is C-O-N-C-R.
No, you check spelling. Check spelling. This is, me, I don't care if you wrote something, even if you wrote it in vernacular, as long as I know that this is not my damn language, much as I speak it nicely. And when I'm marking people, I don't mark the grammar or the spelling. I am not born, this is about my born language. Yes?
Like the question with the spelling, what's the meaning?
Agree. If I don't concur with you, I do not agree with you. If I concur with you, I agree with you. As in unison, I am okay with whatever you are talking about. I like Jonathan's openness. Kabule didn't know, but he was arguing all about